Let's start lecture 27, and the course is corrosion protection methods. We have been discussing on change in environmental factors and associated corrosion protection. That's a broad topic, and last class we started our discussion on effect of addition of oxidizer on the active metal, and then we realized that if we reduce the oxidizer or remove oxidizer from the system or from the electrolyte, definitely we will have a low corrosion rate, and in other way around, corrosion resistance improves, or corrosion protection can be better when the system where or the electrolyte contains no oxidizer, like Fe3 plus or Cu2 plus. Those are strong oxidizers. Then we realized that addition of oxidizers could be, and we actually suggest, we talked about it, that addition of oxidizer could be different in case of active passive metals. It can actually degrade corrosion resistance, or it can actually improves the corrosion resistance if we keep adding oxidizer. And if we keep adding oxidizer at certain critical point or critical concentration level, though the material goes from very active dissolution to a passive state, and then again it can actually go into transpassive zone, where again corrosion rate increases, or it would lead to a poor corrosion protection. So let us look at the influence of oxidizer addition in case of active passive metal with respect to mixed potential theory. Then we would realize that why this situation arises, that addition of oxidizer leads to improvement in corrosion resistance. So let's look at the effect of oxidizer addition on active passive metal. In order to understand this, so we need to understand mixed potential theory. We'll discuss this with reference to mixed potential theory. So let's draw E versus log I. Okay. Now, if it is active passive metal, then for the metal which is dissolving, that will have a pattern like this. Okay. And here this is corresponding to I0 for the metal on metal surface. This is the E equilibrium for the metal. This indicates metal dissolution, and this is going through active zone and then reaching to passive zone. This current corresponds to I passive. This is of course I critical, and we have understood the importance of I critical in order to achieve passivity, and this is my passive zone. This is my passive zone. Right? This is my passive zone. Now, beyond that point, we have transpassive. Okay. Now, if we take a generalized oxidizer, let's say OX, which is oxidizer or oxidant. Okay. and red, let us say it is a reductant. So, ox plus E equal to red. Example. Okay. Now, if the metal is not under passive condition, so then the metal, whether it will reach to the passive level, that is in the I-passive zone, or whether the metal would remain in the active zone, that will be decided by the interaction of reduction polarization line with the active passive anodic part of this particular shape. Now, if we consider oxidant this particular reaction, let us say at a particular level of oxidant concentration, this is the interaction, let us say. This is talking about OX plus E equal to red. So, this is reduction process corresponding to IC or cathodic current density, and this particular point E equilibrium for the ox red. This is I0 for ox on the metal surface, right. The metal surface, that means on the metal surface that reduction process is going on. Now, as I have indicated that if the metal is not in passive condition, then the metal can only reach to the passive zone, which is corresponding to I passive or the current density corresponding to I passive, only if the mixed potential which is developed is in the passive zone. At the same time, the polarization line should not cross the active zone at any point. Now, here what happens at a particular concentration level, so let us say this is the concentration level C1, I develop the particular equilibrium potential that is developed on the metal surface for that reduction process is this one, and corresponding I0 is this for the metal that oxidant that reduction process. Now, it is cutting at this location. So, this will be my mixed potential, which is corresponding to E core, and this is corresponding to I core. And I could see that at this location I have a situation which is IA equal to IC, or the net reduction process rate is equal to net oxidation process rate. So, now in the beginning these two potential will be at these two locations, equilibrium location. Now, the system will try to drag the potential to the mixed potential, and this is basically nothing but the mixed potential. So, this particular potential would go to this location, and then on the reduction process this potential will be dragged to this location, and then we will have a situation where total rate of reduction process is equal to total rate of oxidation process, and steady state corrosion would happen at this location with the rate corresponding to I core. And if I leave the material there, leave the metal there without the influence of any external current, the metal will dissolve at the rate corresponding to I core, and it will stay at active zone. And if we try to plot the polarization where we are actually supplying current from external source, where I am using potentiostat, the plot pattern would look like this. Okay. So, here what happens? It will go like this, it will follow this, right. You see exactly similar pattern what we have shown on the right side this image. And why this happens? For that I think you should visit the earlier lecture series. This is nothing but subtraction of two current densities, IA and IC, or IC minus IA, and that becomes my applied current density, and that applied current density we have to take a log of it and then put it on x axis. So, this particular current is nothing but I applied equal to IC minus IA or IA minus IC, depending on which side it is. The steady state potential would be at this location. So, if we go this way, then it will be IC minus IA, because this current density corresponding to IC is more than IA, and this is my IA. So, like that we can have that I applied and then take a log, and you will see that current density will follow the line which is shown in a brown, little deeper brown color, dark brown color. Okay. Now, if I try to look at, and if I go on top of it, it will be just reverse, whether I applied would be IA minus IC, because this is my IC and this is my IA, and like that way things will move on. And here we are intentionally forcefully taking the potential from this corrosion potential to above corrosion potential or below corrosion potential, and that can be possible in potential stat. But if we do not have external power source, the system will remain at ICOR. Now, we increase the concentration level. The concentration level from C1 it goes to C2, and C2 is greater than C1, and let us say I0 does not change. There could be influence on I0, and that could be very negligible. But if we assume that I0 does not change, which is exchange current density of that reduction process on metal surface for that oxidant. So, if I increase this, definitely E equilibrium would increase. How? In terms of Nernst equation. So, if I follow Nernst equation, E equilibrium equal to E naught plus RT F ln this. So, if we increase the concentration of this, definitely this one would increase, because E0 is a constant, T is a constant, F is constant, R is also constant. So, like that way this potential would keep shifting up, and if we follow the same slope for the cathodic reaction, okay, or cathodic polarization line, let us say it reaches to this point, or let us say if I for our reference this point. So, if we reach to that level, if we follow the same polarization for the cathodic process, it will follow like this. So, this is my new equilibrium potential with reference to C2, and this is with reference to C1, and this is my IC now. Now, interestingly, the mixed potential we can see it is at this location, which is the E core when concentration of oxidant is C2, and for here this is E core with concentration when it is C1. Now, again as per mixed potential theory, this potential is dragged to this location and this potential will be dragged to this location from the equilibrium point. So, when it drags, it will go through this position and come here, okay, the red line. So, this is the typical behavior of that metal. So, that means it will go through active, very active dissolution, and then suddenly it will achieve passivity. So, in this case the system, if you see this corrosion rate and this corrosion, and this will be corresponding to I core when concentration of oxidant is C2, which is nothing but IP. And here in this case it was I core corresponding to C1. So, definitely I core corresponding to C2 is less than I core corresponding to C1 concentration for the oxidant, because in case of C2 the polarization line cuts the anodic part in the passive zone and it does not cut, and it crosses the I critical also. Since it crosses I critical, no unstable passivity will be achieved, it will achieve stable passivity. And if that stable passivity is achieved, after that you take the material out and then put it back in the same medium, you will see that the corrosion rate would be still that I passive, corresponding to I passive or very low corrosion rate. So, that means you have actually made the material passive, and that passive material will hold passivity if we do not disturb the passive surface by scratching or doing some mark on top of it. So, that material will remain at this location with the corrosion rate corresponding to I passive. And we could see that the corrosion rate actually moved from this to this. So, there is a huge decrease considering the log scale of that current density, fine. Okay. So, when we have increased the concentration of oxidant, in case of active metal we could see the corrosion rate gradually increases, but here initially corrosion rate increases and then suddenly once the cathodic polarization line cuts the anodic line in the passive zone, we get stable passivity. And this does not happen like that, we can choose that particular concentration in such a fashion that it happens immediately or quick passivity is achieved. For example, if we gradually increase the concentration along this line, okay. So, let us say I put a concentration at this location, let us say at this location, fine. So, that time if I draw that line, so this line which is corresponding to cathodic polarization and this is corresponding to E equilibrium, let us say concentration is C prime or C3 let us say, and C3 is more than C1, but it is less than C2. Okay. So, that case I could see that at 3 location I can maintain mixed potential, okay, where I could see that total rate of cathodic reaction is equal to total rate of anodic reaction, because at those location IA equal to IC. So, in those cases, as I have discussed in the previous lecture, that in those cases generally the active zone will be selected, which is corresponding to this particular point, and it will have a rapid dissolution. So, the stable passivity will not be achieved and it will maintain in the active zone. Now, gradually like that, if we keep increasing the concentration, okay, increase the concentration gradually, at one point if I consider this particular polarization plot, which is the gray one, this particular thing, it is just crossing the I critical, if you see at this location, okay, just crossing. So, that means that should be the critical concentration, let us say the concentration corresponding to that is C star, okay, or E equilibrium C star. So, that is the critical concentration where I would be able to cross the I critical, just cross the I critical, so that it can achieve stable passivity and it will reach to the passive zone, and then corresponding current density for the corrosion rate will be I passive again. And then if you keep increasing the concentration till it reaches to this level, it reaches to this level. So, that means it actually crosses the ET or transpassive potential. So, let us say this is ET, transpassive potential. Then after that, if you increase the concentration, again it will start increasing, the corrosion rate for that metal will start increasing, because you see the corrosion rate is gradually increasing along this line. So, this behavior can be seen in metals and alloys in different mediums. Now, as we see that till this E critical point, I will see a rapid dissolution and active dissolution, and these happens, for example, if I consider now, if I try to plot the corrosion rate as a function of concentration, you will see that the corrosion rate till I critical, till C critical is gradually increases, and then once the concentration reaches to C critical, that is the concentration, immediately the corrosion rate drops. Let me just plot it like this. Immediately corrosion rate drops, which corresponds to I passive, and then after that you keep increasing it until unless you reach to the concentration corresponding to equilibrium CT, okay, which is the junction point and exactly the cross point between ET, which is a transpassive potential, and I passive. So, then it will keep maintaining the passivity, and then once this CT is reached, which is corresponding to the potential where that polarization line for the cathodic part cuts the anodic part at ET, or potential corresponding to transpassive potential. So, there again the corrosion rate will start increasing. So, this will be the typical plot, the corrosion rate versus, if I consider the corrosion concentration of oxidant. So, this is concentration of oxidant concentration, right. Now, if I mark it at several zone, this is zone 1, this is zone 2 and this is zone 3. So, we can have several combinations. So, case 1 where zone 1 is noticed, or let us say zone 1. So, that time we can see such behavior like Monel in HCl plus O2. Here O2 is the oxidant. Then we can have this behavior copper in H2SO4 plus O2, Fe in H2SO4 plus O2. So, that means all the time it will be showing active behavior. So, that means increase in concentration will have increase in corrosion rate, or the protection will be hampered. So, it will have a rapid dissolution. Now, why it happens? Because the entire region stays in this location, where this is active zone. Now, once we cross C critical, the concentration of oxidant, it will achieve passivity, which is nothing but this one we have seen before. We have explained this. So, then increase in concentration would not have any effect. It will maintain I passive at a low corrosion rate. So, this particular case we call it, this particular case can be achieved for a material with a quick passivation ability. And once we have this, we can take the material out, again put it in the same medium without disturbing the surface, it will maintain that low corrosion rate. So, that behavior, so it can have it can have only this, then it can have this. So, that means zone 1 and 2, which can be observed in case of 18-8 stainless steel in H2SO4 plus Fe3 plus. So, Fe3 plus is basically here the oxidant, or titanium in HCl plus copper 2 plus, and here copper 2 plus is the oxidant. Now, you can also have only 2, zone 2. So, zone 2 can be observed, like let us say I have 18-8 in HNO3. Since HNO3 is a strong oxidant and it breaks into nitrous oxide or nitrogen oxide, N2O or NO2, as well as H2O, depending on the concentration of HNO3. As we increase the concentration, its oxidizing power also increases. Now, in this medium, this particular 18-8 stainless steel immediately passivates. It takes no time to reach to the passivation. So, that means it reaches to this zone 2. Okay. So, similarly, we can have Hastelloy, which is a nickel base alloy in FeCl3. So, here 3 plus, which is the oxidant here. So, there also it gets to the zone 2, which is the passive zone immediately once you dip it in that medium. So, this is zone 2, only the metal in case of a zone 2 is observed. So, that means that metal would be extremely resistant to those kind of situations, and it will have a strong passivity. Now, we can actually have a situation where zone 2 and 3 are observed. So, zone 2 and 3, those can be observed. This particular situation can come up in some metals and alloys which are quickly passivating, but that they stay this particular passivation stays very close to the transpassive zone. So, then definitely with a little increase in oxidant, it reaches to transpassive zone. In this case, for example, if something some oxidant process, let us say this. So, this is another concentration level of oxidant. If it in case of that metal, if it is starting with this, so that corrosion rate would be here, but you see it is this is staying very close to transpassive zone. So, then definitely with increase in concentration of oxidant, it can reach to transpassive. So, again corrosion rate can increase. So, that is the situation in case of zone 2 and 3, which can be observed in case of 18 chromium 8 nickel in HNO3 plus Cr2, which is a chromate kind of oxidant, which is a strong oxidant. So, that case it can happen like this. Now, in some metals and alloys, it can actually have all 3 zones. So, that means it can have this one, then this one, this particular zone, and then third zone. So, for zone 1, 2 and 3, all 3 are noticed. In that case, we can have an example 18 chromium and 8 nickel stainless steel in hot HNO3 and H2SO4 acid mixture. So, now in this case what happens, if we change the content of HNO3, which is the oxidant, and keep increasing the oxidant content with reference to H2SO4, the material will change from active zone, which is the zone 1, then this is the zone 1, then it will go to passive zone, and then it will go to zone 3, which is the transpassive zone. Now, it will go from this location to upward, and then finally it will achieve all those, it will show up all those zones, but it depends. This particular case is decided by relative content of HNO3 and H2SO4. So, this behavior shows when HNO3 content gradually increases over H2SO4 content. So, that case we can see all three cases. Now, it is very important for the passivity, active passive metals, and all those situations actually are typical for active passive metals. And in case of active passive metals, it is better to stay at zone 2. That case, it can actually provide a very good protection, because I passive is the lowest temperature, lowest corrosion rate observed in case of active passive metals. So, now we could see that removal of oxidant or removal of oxidizer is helpful in case of active metal all the time, as we have observed in the last lecture. But removal of oxidant may not be effective to provide better protection in case of active passive metal, rather their addition of oxidant can be helpful. So, now for example, one particular metal shows active zone. Now, if we add little bit of oxidant, it can take it to passive zone, just like 1 and 2, zone 1 and 2, where from it moves from zone 1 to 2, and 2 is the passive zone, and it actually remain at a very, very low corrosion rate position. So, that means it has the maximum corrosion resistance in that particular condition. So, that it is decided by the electrolyte, the nature of oxidant, as well as the interaction with the metal. Okay. So, now we could see the behavior with reference to oxidant, and now we can conclude with this, that addition oxidant can be helpful for corrosion protection. And we will see in case of inhibitor, sometimes in inhibitor we add oxidant, so that the passivation is possible, quick passivation is possible. So, this oxidant removal is not helpful here, rather oxidant addition is helpful here. So, and this is typical of active passive metal. So, let me conclude like this. So, now as we have seen that we have discussed about addition or removal of corrosives, and most of the cases removal of corrosives work better for adding extra bit of corrosion resistance as well as corrosion protection. But in case of active passive metal, addition of oxidant or oxidizer can be helpful. Okay. So, we will discuss on this very topic, a broad topic, which is change in environmental condition or factors for corrosion protection, and next class we will talk about effect of velocity as well as temperature, and then we will end our discussion on change in environment. We will talk about addition of inhibitors. Thank you.